Okay, today we are starting Unit 10, which is called stoichiometry. Last unit is a good preview for how this unit is going to go. And so for today, this section is going to be called defining stoichiometry. And you just heard me say it twice. I don't want to hear stoichiometry or stoichiometry or stoichiometry. Stoichiometry. The CH sounds like a K. All right, stoichiometry, definition. You have a vocab quiz this Friday. Is the study of quantitative relationships. Between the amount of reactants and products. In a chemical equation. I want to look at this word quantitative. Does this mean descriptions like color, smell, or does it mean numbers like amounts? Numbers. There's quantity versus quality. Like your English teacher might say, I want quality of your writing, not the quantity. That means I don't care how much you write, it needs to be good. So quantity is numbers. Stoichiometry is based on the law of conservation of mass. The law of conservation of mass simply states, however much you put into something, you need to have that same amount on the other side. So, for example, if Jade has a 1,500 pound car, that's 3/4 of a ton. 1 ton is 2,000 pounds. So this is actually a pretty light car. And she just went grocery shopping. And her groceries probably total about 20 pounds. 20 pounds of groceries. And Jade weighs about 130 pounds. How much total weight is in the vehicle? So if you have 15,000, or 1,500, excuse me, plus 20 pounds, plus 130 pounds. What does that equal? 16 what? 1650. Guys, this is the law of conservation of matter. If Mr. Max up here has 4 quarter pounders of cheese, how much weight did he just gain? He gained 1 pound. It's that simple. It's that simple. If Dennis is wrestling and he's going in for a weigh-in, if you ever watch weigh-ins for UFC, whatever, they strip down to their underwear because your clothes weigh stuff. So if Dennis is or John Dennis, he's not here. If he's a wrestler and he takes off his shorts and he takes off his shirt and he takes off his shoes, and he takes off his belt, and all of his clothes together weighed like 7 pounds, then you would have like clothing, 7 pounds. Or let's see. You would have Dennis, or John Dennis, which would be like 170 pounds, and then you break that up, you would have 7 pounds of clothes, and then you might have 163 pounds of human. So this would be a breaking down problem. This is the total. This is the person and their clothes. You break that up, you got clothes, you got the person. So this all abides by the law of conservation of mass. However much you put on one side, you need to have the same amount on the other side. Another example could be with photosynthesis. 6 moles of carbon dioxide react with 6 moles of water to produce 1 mole of glucose and 6 moles of oxygen. Jade, can you take a look at the entire reactant side, this whole side here? How many moles of carbon do you see? 6 moles of carbon, correct. Max, how many total moles of hydrogen do you see? No. You have to look at the coefficient. 12. 6 times 2 is 12. Kendall, how many moles of oxygen are there? Carefully count. No. You have to look at both items in the reactant side. What is 6 times 2? And what is 6 times 1? So what's 12 plus 6? 18. Okay, let's take a look on the product side. Colby, tell me how many total moles of carbon are there in the product side? Are you? Yes, okay, that sounded more confident. 6 moles of carbon. Nick, how many moles of hydrogen are there on the product side?
12.
Yep. And Emma, how many moles of oxygen are there?
6.
Nope. What's wrong? You can't see anything? Why not? You didn't bring your glasses to school. So how do you expect to survive today? Why don't you move over there behind Jade or Max? There's 2 open seats. Can you see better from there? Carson's gone back to e-learning, so you can sit in her seat if you need to. Okay, can you see that now?
Yeah.
How many total moles of oxygen are there? What?
Yeah. I'm supposed to multiply the 6 times 12, right?
The 6 and the what?
The 6 times 12.
Where are you getting 6 times 12?
Because there's 6 oxygen.
Where are there 6 oxygens? What molecule? Glucose or oxygen? So where are you getting the 12 from? No, I'm just asking you how many moles. I'm not asking you the molar mass. I'm just asking you how many atoms or how many moles are there?
6.
There's 6 there, but what about the other side? Here.
8.
8? 6 times 2 is 8? Okay, we're having a little trouble here. This is the second time it's come up in this class, so let's get this solved because all of you need to know there's 6 moles of oxygen right there. Does everybody see that? What is 6 times 2? 12 moles there. So, Emma, what is 6 plus 12? 18. Do both sides equal each other? That is the law of conservation of mass demonstrated. Let's do another one. Kendall, how many moles of iron are there on the reactant side? How many? What are you saying? 4. I didn't understand you. How many moles of oxygen are there? Yes. Good. Can you tell your classmates how you got 6? I bet there's someone here that didn't know how you got that. 3 times 2 is 6. Okay. Emma, how many moles of iron are there on the product side?
4.
How'd you get that?
3 times
2 times 2 is 4. And how many moles of oxygen?
3.
No. This 2 distributes across all of it, Emma. So try again.
6.
How'd you get that?
2 times 3.
2 times 3 is 6. Jade, are both sides equal?
Yeah.
That is, so let me ask you this. Is the law of conservation being observed here? Yes, it is. The law of conservation of mass is being observed. What does that mean, it's being observed? It means that both sides equal each other. If I put 4 moles into it, I'm getting 4 moles out of it. If I'm putting 6 moles of oxygen into it, I'm getting 6 moles of oxygen out of it. If Max eats 4 quarter pounders with cheese, his entire body mass will have gained 1 pound. But then we obviously have the processes of digestion and toilets, and I'm not going to get into all that. All right. Now, let's talk about relationships that you can get from a balanced chemical equation. I'm going to use this one that we just did. Oops. We have 4 iron, 3 O2, 2 Fe, 2 O3. Okay, here's where I need you guys to help me out. Let's put this in terms of actual names. Okay, I want the actual names of the substances. What is Fe? Correct. What is O2? Oxygen. And what is Fe2O3 called? It's not iron oxide. Iron is a D block metal. It can have multiple charges. What is the charge of the iron?
Iron 3 oxide.
How do you know it is iron 3?
Because oxygen has -2 charge, and so -2 times 3 is -6. And so iron has 2, and so the only way to balance that is if iron has a positive 3 charge.
All right, if that went completely over your head, let me slow it down. You guys cannot tell me by just looking at that iron, oh, that's a positive 2 iron. No, how do you know? Well, okay, it's positive 3. How do you know? What Arshawn did is he looked at the oxygen first. And he said oxygen always has a -2 charge. He said there are 3 oxygens there. So -2 times 3 is -6. That means that these 2 irons must equal positive 6. Well, there's 2 irons. So something times 2 must equal positive 6. And that something must be positive 3. So those irons have a positive 3 charge. So they are called iron 3. So this whole compound is called iron 3 oxide. Okay, that's for names. Now, I want you guys to tell me this in terms of atoms and molecules. Or let me rephrase that. Representative particles. Rep parts for short. What is iron? Is iron an atom, ion, formula unit, or molecule? So I have 4 what of iron? I have 4 atoms of iron. Good. It's an atom. How about oxygen? What is that? O2. A what? Molecule. A nonmetal and a nonmetal. So how many molecules of oxygen do I have? 3 molecules of O2. And how about iron and oxide? I'll give you a hint. Metal and nonmetal. Formula units. How many? 2 formula units. Fe2O3. Okay, now I want you guys to tell me this in terms of moles. How many moles of iron are there? 4 moles of iron. I'm going to start calling people individually. Derek, how many moles of oxygen gas are there? You're thinking atoms. You gave me that's number 6. That's total oxygen atoms. I'm asking you how many moles of the oxygen molecule, how many moles of O2 are there? There are 3 O2s. That's right. So 3 moles of O2. Whoops. 3 moles O2. And Scout, how many moles of iron 3 oxide are there? 2. 2 moles of Fe2O3. Nice. Okay. Now, I want to know this in terms of molar mass. This will be the last one we do. So I'm going to let you guys figure this out. I'll give you about 1 minute. I need you to calculate the total molar mass of both sides. Keep in mind, keep the coefficients and the subscripts in mind. Max, get to it. Where's your calculator? Again?
Yeah.
Do I need to email your mom every day you forget it?
No.
Bring it. If you don't bring it tomorrow, I'm going to tell her again. Round your answer to the nearest 10th for me, please. The 10th place. Okay, here's what you should have. 4 irons all together should be about 223.4 grams per mole. 3 moles of oxygen should be about 96.0 grams per mole, O2. And 2 moles of iron 3 oxide should be approximately 319.4 grams of Fe, or grams per mole, excuse me, of Fe2O3. Did you guys get that? Yes, Nicole.
So if it's grams per mole, why wouldn't it be like 56.6 for oxygen? Because it's 4 moles instead of 1 mole.
There's 1 mole of iron, and then what was it? 50.
56.6 would be 1 mole of iron. Is it correct? Is the one actually for 1 mole?
Yeah, and there's 4 moles up there in the.
But it says like you put grams.
Okay, so then we can do, yeah, per 4 moles. That would make sense if you want to get down to that. But if I have 3 moles altogether, so let's just do this then. Let's just put grams. Now, I want you guys to do the total reactant and product side. So you just add the 2 reactants. What is 223.4 plus 96? You should have 319.4 grams. This is your total reactant side. So for all of your reactants, you get 319.4. How many products are there? 1. Where are you getting 2?
There's 2 of them. 1 reactant.
1 reactant. 319.4 grams of product. Timothy Kirk, is the law of conservation of mass being observed here? How so? The amount of the reactant is equal to the amount of products. That proves that the law of conservation of mass is being observed. Okay, guys. Let's see, I want to... All right, here we go. Let's start doing some examples here, some actual problems. How do I want to shorten this up? Express the combustion of propane in terms of A, representative particles, B, moles, and C, mass. So we'll do this one together. First, I need to help you actually construct the combustion of propane. Do any of you recall what propane is? What is the formula? Okay. It is C3H8. So propane is C3H8. That is one of your reactants, and it is a gas. Now, this is a combustion reaction. What gas do you need in order to combust fuels? Tim? You need oxygen, O2. That is a gas. This is, guys, what I'm going over with you right now is stuff from Unit 8, which is the last unit we did before Christmas. Now, let's see how well you remember that stuff. Because propane contains carbon, it's right here. I mean, pow, there's 3 of them. What are one of your products, Arshawn? CO2 is a product. Because your main reactant, propane, has carbon in it, one of your products is going to be CO2 gas. And what is the other product in a combustion reaction? You have CO2, and what is the other one, Francis?
Water.
H2O. Very good. Now, I want you all to take a long, hard look at this equation. Is the equation balanced? Tim is shaking his head. Anybody else? All right. So here's what you need to do. Step 1, balance the equation. Now, I'm hoping that you can get good enough at this where you don't have to do the little scoreboard that I taught you how to do. But if you got to do it, you got to do it. I'm never going to tell you don't use the scoreboard. But if you have to do it, you have to do it. So can anybody maybe tell me what this is, what this look like being balanced? Basically, what's the ratio? What to what to what to what? Anybody know? Let's take it one at a time. Jade, how many carbons are on the left side? How many carbons are on the right side? So what coefficient do you think we should put in front of carbon dioxide to get the carbon number balanced? I agree. So throw a 3 in right there. Okay, so far so good. Now, Derek, how many hydrogens are there on the left side? There are 8. How many are over here on the product side?
There are 2.
How can we bump that 2 up to an 8? I agree. Put a 4 there. Very good. Now, let's see. Adam, can you count how many total oxygens are on the product side after we basically balance the product side? No, you're not looking at the entire product side. You're only looking at one substance. All you did is look at the carbon dioxide. No, where are you getting 12 from? Tell me.
3 times 2 is 6.
That's right.
There's 4 oxygen.
Okay, so you're saying 6 plus 4 is 12? 10 is better. Okay, so there's 10 total oxygens on the product side, Adam. How many oxygens are there on the reactant side? How can we bump that up to 10? Put a 5 coefficient in front. You are correct. Good. Okay, so it is balanced. If you guys need to do that scoreboard, I'm never going to tell you not to. You just put the C, the H, and the O here. C, H, and O, and you just you do your tally marks, and you eventually get it figured out. Okay. Now, let's get this in terms of representative particles. So this will be part A. Take a look at the top. Propane, you got carbon, you got hydrogen. Is that a molecule or a formula unit? Is it a metal and a metal, or excuse me, a metal and a non-metal, or 2 non-metals? 2 non-metals. So how many molecules of propane are there? 1 molecule of C3H8, correct? Plus, let's move on to O2. Molecule or formula unit? Oxygen and oxygen. Is that a metal and a non-metal, or 2 non-metals? How many molecules of oxygen are there? 5 molecules O2. Okay? Take a look at carbon dioxide. Metal and a non-metal, or 2 non-metals? Non-metal, non-metal. So what is that? 3 molecules CO2. And what is water? Metal and non-metal, or 2 non-metals? 2 non-metals. So what is that? A molecule or a formula unit? A molecule. 4 molecules of H2O. So that is part A completed. You write it in terms of whatchamacallit? Representative particles. Brain fart. Okay, let's go to part B. It should be the same thing. You just do the same thing, guys, except use the word moles. 1 mole propane plus 5 moles O2 yields 3 moles CO2 yields 4 moles H2O. Okay? And now here is the part that requires the most work. I need you to find the masses. So what is the total mass of that 1 mole of propane? Add up the 3 carbons, add up the 8 hydrogens. Tell me that first. So basically 12 plus 12 plus 12 plus 8. Kevin?
44
For propane? All right. Now, you have oxygen. 1 oxygen atom is 16. O2 is 32. How many moles of O2 are there? 5. So what is 32 times 5? What'd you get? 160? If you are sitting in your desk, you're like, wait, what? Look at the periodic table. Oxygen is 16, correct? How many oxygens are there in O2? There's 2. So doesn't it make sense that O2 is 32 grams? And then how many O2s are in our problem? There are 5. So when you have 5 O2, it's 32 times 5, which is 160. That's where we got it. I have no problem slowing it down and let you all see where we're getting these numbers from. Okay, let's go on. CO2. 2 oxygens is 32, plus 1 carbon is 12. 32 plus 12 is 44. How many CO2s are there? How many moles of CO2 are there? Derek, wake up. So what is 3 times 44? 132. And I've asked you to memorize water. What is water? Just memorize it, guys. It's going to go a whole lot faster. 18. How many moles of water are there? 4. So what's 18 times 4? Okay, now I need you to add up the entire reactant side and the entire product side. What is 44 plus 160? 204 grams of reactants. What is 132 plus 72? 204 grams of products. Is the law of conservation of mass being observed? Yes, you proved it. This is how you prove it. Both sides have the same amount of mass. Any questions on that? What we are doing over the next week is we're doing practice problems like this so you actually have the stages to study to learn how to do them on your own without me there to help you. Okay, let's move on. We have about 6 minutes left, so let's get to mole ratios. I want you to take a look at, or when you do mole ratios, you refer to the coefficients. The coefficients are the numbers in the front of the molecules, the atoms, the formula units, the ions. They can represent, coefficients can represent representative particles, and they can represent moles. They can do both. So I'd like you to take a look at this example. Okay. Here's what I would like you all to do. I want you to write all the possible mole ratios. I'll do one set for you. Let's start with 2 moles of potassium. Jade, for 2 moles of potassium, how many moles of bromine are there? Look at the coefficients only. The coefficients are the numbers in front. 1. When you don't, in this class, when you don't see a number, what is the number? Right. 1 mole of bromine. Jade, for 2 moles of potassium, how many moles of potassium bromide are there?
2.
Correct. I guess I'll just go through the whole thing with you guys. Colby, for 1 mole of bromine, how many moles of potassium are there? Correct. And Colby, for 1 mole of bromine, how many moles of potassium bromide are there? For 1 mole of bromine, how many moles of potassium bromide are there? Where do you see 1?
2.
Where do you see that? In front of the what? What is potassium bromide? Give me the letters. Correct. Sometimes I want you guys to prove to me you're seeing what I'm seeing. Okay, Nick, for 2 moles of potassium bromide, how many moles of potassium are there?
2.
Correct. And Nick, for 2 moles of potassium bromide, how many moles of bromine are there?
1.
Correct. Okay, that is correct. And we could have done the same things with formula units, molecules, and atoms. All right, so here is the last thing I want you guys to do. I want us to bring back propane in the balanced equation. I'll go ahead and balance it. Here's what I want you guys to do, and you can do this till the bell. The bell might cut you off. I want you to write every possible molar ratio in this equation, just like what I did for you in the previous problem. You should have a total of, let's see, 1, 2, 3, 4, or 1, 2, 3, 4, 5, 6. You should have a total of 12. 12 total ratios in the equation for propane. Do this to the bell. I want this completed when you walk into class tomorrow. I don't want you doing it when you come into class tomorrow. I want it done by the time you walk through my doorway tomorrow. And this is where we will start tomorrow. If you still have no idea, I don't know what you're talking about, Mr. Thorson, here's what I mean. 1 mole of propane is equal to 5 moles of O2. 1 mole of propane is equal to 3 moles of carbon dioxide. And 1 mole of propane is equal to 4 moles of H2O. 3 down, 9 to go. This is the tedious part. Every year, this is the tedious part. But you have to be able to accomplish the tedious part. If you can't do that, then you can't do the hard stuff. Okay. Hasta la vista.